Well, then should we start?
Yeah, I guess so. I mean, I guess the good. And we can see that.
Yep.
Yep.
Okay. Okay, so this topic stands from a long-standing curiosity in discrete Fourier transform, uh, and mainly because I wanted to get a bit better understanding of its underlying principles. I'm not sure why, but I did. So uh, about 3 months ago, I guess it was, I decided to, well, for whatever reason, the opportunity presented itself, so I started to read it, and then here we go. I'm dragging you guys in with me. So to start off with, as like Dave says to with his presentations, really, I am not a DFT or a discrete Fourier transform expert by any stretch. So the information I'm sharing is based on what I've learned, and it's all in this presentation. So if you have any technical questions, I'm not likely to have the answers. I might, but I'd be surprised. While there's many resources available, like YouTube videos, they often go deep into the math. And since Fourier analysis is mathematically intensive, that's understandable. So really the goal of this talk is to introduce the discrete Fourier transform, explore its practical uses, and maybe inspire us to how we as hobbyists can apply it to in our projects. And maybe it might spark some interest for you to learn on your own. Okay, so in the time domain, we see how the signal changes over time. The frequency domain gives us a different perspective. And instead of showing the signal shape, it shows what frequencies are present in that signal. And the tool that makes this conversion is the discrete Fourier transform, or DFT. DFT breaks down a complex signal into a set of sine waves, each with its own frequency, amplitude, and sometimes the phase as well. It's an important in real-world applications like filtering, communications, noise analysis, that type of stuff, because many signals can look similar in the time domain, but have a very different frequency content. You can kind of think of this like a shining a white light through a prism. The DFT reveals the individual colors, or the frequencies, if you will, that are hidden inside that signal. So discrete Fourier is a mathematical tool that takes a signal and shows what frequencies make up that signal. And you can think of it like this. A complex signal is like a musical chord. And it sounds like one thing, but it's actually made up of many notes. And the discrete Fourier transform tells you which notes or frequencies are in that chord and how loud, or the amplitude, each one is. And this helps us because we now have a better understanding of what's making up in our signal. So here's just really the analogy I used of the white light in the prism. So every signal, no matter how complex, can be seen as a combination of many waveforms, each with its own frequency, amplitude, and phase. And the process of breaking down a signal into its components is called frequency analysis. And the result is the frequency spectrum. And the spectrum acts like a blueprint for the signal. It shows what frequencies are present and their respective amplitudes. Signals are theoretically continuous, but in practice, we sample them at regular intervals, for example, 1,000 times per second. And discrete Fourier transform works only on these discrete samples, not the continuous waveform. Real-world data is finite and typically sampled in blocks like 256, 512, or 1024 points. And the DFT assumes that each block represents a repeating waveform cycle, which helps with the math, but can be problematic if the signal doesn't repeat cleanly within the sample window. So the smooth line here, it's representing a sine wave that we're analyzing. And you now notice the black dots sitting on the sine wave. And these represent the sample values taken at specific, evenly spaced points in time. And this is how we digitize the signal for computer to process. We're converting an infinite signal into a finite sequence of data points. And now the spacing between these dots is labeled delta t. And this is called the sampling interval, or the time between each sample. And the smaller the interval, the more data we collect per second, which affects how accurately we can represent the original wave. We don't take the whole waveform, only a section of it. And that section is shown in the shaded gray area containing n samples. And this is a practical necessity as we cannot compute on infinite data. So we'll focus on a slide. So here's the core idea. Discrete Fourier transform only works with a finite set of numbers. It doesn't see the original continuous signal, just this extracted portion of it. And that's why it's called discrete. And because we analyze only a chunk of data at a time, the results the DFT tells us about the frequency content within that window. And understanding this limitation is important. And it's why techniques like and zero padding exist in the signal processing. So the DFT outputs a list of frequencies present in the analyzed signal segment. And these are the frequency components that make up that signal within that time frame. Discrete Fourier sorts the signal into frequency bins, and each bin shows the strength of the particular frequency, like how much of 100 hertz or 200 hertz, etc., is present. Including more samples, in other words, a larger window, improves the frequency resolution, allowing us to distinguish between closely spaced frequencies. A bigger N means narrower bins and a finer detail. And then, of course, with fewer samples, frequency bins widen, making it harder to separate close frequencies. And this is a common issue in fast real-time analysis. A longer window provides better frequency detail, but it assumes that the signal remains steady. If the signal fluctuates quickly, a long window may blur the results. Okay, so what's the difference between DFT and FFT? So discrete Fourier transform is the fundamental mathematical idea behind transforming signals from the time domain into the frequency domain. It's about understanding what frequencies are present in a block of data and how strong they are. The discrete Fourier transform is defined by a formula and can be applied to any chunk of sampled data, no matter how small or how large. Now, fast Fourier transform doesn't change what discrete Fourier does. It's just a more efficient algorithm for computing it. You might think of discrete Fourier transform as the concept and the fast Fourier transform as the clever trick that makes it practical in real-time applications like audio, communications, radar, etc. In other words, discrete Fourier transform is like a longhand calculation, while fast Fourier transform is like using the calculator to get the answer much faster. So here's a summary of what I've talked about. I won't go into any real detail here, but it's basically, one's fast, one's slow, one's flexible, less flexible, that kind of thing. So this slide shows why discrete Fourier is so powerful. In the time domain, here a 1 kilohertz signal is mixed with distortion and noise and looks like an unreadable mess. But in the frequency domain, the discrete Fourier reveals a sharp 1 kilohertz peak with a noise floor beneath it. And pulling out of this structure from the chaos, this is exactly how weak signals like FT8 or whisper are detected, or how software identifies a note that Eric played in a noisy audio track, right? And the DFT makes that hidden frequency visible.
Or on a theremin.
Well, yeah, that's why it's a noisy audio track. This is just another example of DFT processing on the two upper ones there. You've got a nice clean sine wave in your frequency spectrum. It's nice and clean with the one peak. And then you get a chaotic kilohertz waveform with all kinds of frequencies in there. And then your frequency spectrum, but it breaks it down. Okay, so applications for hobbyists. Well, spectrum analysis, audio signal processing, RF signal decoding, noise detection. And here's a little bit more detail for us. I think this first one's a good one. A spectrum analyzer functionality. Use discrete Fourier to build a simple PC-based or microcontroller-based spectrum analyzer. That one shouldn't be too difficult to do. Signal purity and harmonic analysis. Again, we want to check our oscillators, our transmitters for harmonics. We can use the DFT or FFT to identify that. Filter design. That could be, that's not a bad one. I'm thinking of this more in the audio for what I'm kind of starting to do right now. But the FFT will be handy there because you can identify what signals are there and what you need to. You can design your filter around that. And here, just a continuation of other things that we can do: modulation analysis, front end receiver testing, audio band, baseband debugging, etc. Okay, now what was I going to do here? Oh yeah, and to actually use the discrete Fourier, or more commonly the fast Fourier transform, you can start by capturing your signal in the time domain, and that just means recording it, how it changes over time. And you could do this with your oscilloscope or your digital oscilloscope, which I think pretty much all of us have. A sound card, a microcontroller with an ADC like an Arduino or a Teensy, or with a software-defined radio. Next, you then take the fixed number of samples, say 256 or 1024, and you can think of that as your snapshot of your waveform. And then you run the FFT. It's usually in software like Python with NumPy, MATLAB, Octave. And many of the audio or SDR tools have FFTs built right in. And then the output is the frequency domain view, a plot of the amplitude versus frequency. And that's where you can clearly see what frequencies are present and how strong they are. Okay, so now that you have the result, you can use it to display in the spectrum, log the data, or take action on it. And an example here would be detect a tone in a noisy signal, identify harmonic distortion, automatically adjust a filter in software and hardware. And I think that's a pretty cool idea that we should think about in some of our projects. Perform an FFT on an audio signal to display the frequencies and amplitudes, enabling the identification of frequencies to enhance or reduce. And that particular one is kind of what I'm working on off and on right now. And this is just an image of what I just talked about, grabbing the signal, sampling it, and applying the DFT, etc. So here's some software tools that you can try. I won't go into any detail here really, but I think we're all familiar with Audacity and what that does. You can import or record the audio, and it has an FFT spectrum display on it. GNU radio with some SDR hardware, RTL, SDR, hack RF. I think, Kevin, you got a Lime SDR. Probably haven't touched that one for a while, but there you go. Python with NumPy, SciPy, and MATLAB libraries. I've not played with really any of that stuff, although Python's in the background with GNU radio. But and then Octave and MATLAB, and those I've not played with at all. Probably won't either unless somebody here knows all about it and knows the easy way of doing it. Hardware, RTL dongles. I think most of us have that, and probably hack RF. There's a few with the hack RF. Teensy 4.0, 4.1, they tell me, with the audio library is good. Oscilloscopes with the FFT mode. Davis should be our resident expert on using oscilloscopes FFTs, since he sent his essay out for repairs a while back and had no choice but to use the FFT mode on his scope. And then the USB sound cards. Okay, so some of the experiments you can do is build a tone generator and verify with FFT, create filters and measure it. Use DFT to detect when certain signals are present, like in a tone decoders, etc. Analyze the harmonics of a square wave or oscillator. Record RF samples using SDR, and then viewing the spectrum. So in addition to suggesting some experimental activities you can try on slides 23 through 27, I just want to emphasize the following key points. The discrete Fourier transform converts time domain data into meaningful frequency domain insights. And you can explore and understand DFT without the need of expensive equipment. DFT is the foundational principle behind many of the instruments we already use, and gaining an understanding of discrete Fourier can help us design and improve our own test gear. So here, like I said, we're just some experimental ideas that we can work with on our bench or try on our benches. FFT of synthesized signals, learning the harmonic content of signals and how square waves contain odd harmonics. Visualizing aliasing, that'll be a good one to try. Sample a sine wave and then with using it and trying that at different sampling rates on the ADC and then observing the results. And of course, with GNU Radio, which is free, that should be relatively easy to do. DFT by hand. I don't think I ever tried that one. I might have dabbled a little bit in it, but only because Dave made me do it, or he already done something like this in Excel and sent me the spreadsheet. Measure the responses of the filters and noise versus signal analysis, and that one there crops up every once in a while of late, anyways. Trying to get a handle on noise, how to measure it, etc. And decode simple signal, modulated signals, transmit AM or FSK using your tone generator, and then analyzing how the modulation affects in the spectrum. Okay, in summary, discrete Fourier transform turns time domain samples into your frequency domain insights, and you don't need expensive tools. It already underpins many instruments we already use, and understanding it can help us build better gear. So here's a setup of mine. This was taken a few years ago. This would have been during our Let's Build. Oh, I know who was missing. Frank. I didn't see him there. Anyway, this reminded me because this was the LBS project. I can tell that because on the SA, I can see the frequency of the center marker is 4.9 megahertz, and that's what we used on the LBS projects. But you can see on the oscilloscope, try and figure out what frequency you've got there. And of course, on the SA, you can quite clearly see what the different frequencies are that are making up that signal. In fact, if you look closely at the oscilloscope is picking up 6.47 kilohertz. So that's what we got going on there. And that's all I've got. Okay.
YouTube uses DFT to compress video stuff too, apparently.
Oh, yeah?
Yeah, it can be used for that kind of thing as well.
Well, I guess, if somebody wants to figure out a way of saving space, considering how many videos are up there and how much space that all takes, it's a wonder we haven't melted the planet yet, but anyway.
Yeah, exactly.
Okay. So that's all I got on that particular subject. I hopefully it didn't bore too many people to death. But one thing that came out of there is I'm working on is an audio spectrum analyzer. And I finished off the board the other day, and I sent that off to JLC PCB. So we'll see what comes back and see what happens when I put it together. But that's going to be running on the Arduino as well. Drew, you had a question?
Well, it was just interesting to me. You mentioned Audacity does this.
It's been a long time since I've looked at that program, but I believe you can record. You can record the audio or whatever.
You can,
and
yes.
There's an FFT display on that, I believe, is there not?
I don't know. The reason that intrigues me, we're about to use Audacity for bird call analysis.
Oh, okay.
And we're using an AI to do it, but I can read the files using Audacity, which is hard to do. It's proprietary under normal circumstances, but they didn't figure on Audacity. I will take a look and see what I find out, because that's kind of interesting. If I could break, any call down into its frequencies, it allows me to differentiate a little better. There's a great argument about an animal we have at work. And the argument is this animal actually that animal? Oh. And it comes down to a spectrum analysis of the call.
Can you have you not tried Merlin,
That's
Huh?
what I was going to say.
the phone
Merlin?
app? Yeah, the phone app.
No.
Oh, it's a good one.
I was using it all summer. It's fantastic.
Well, this is it's between a spring peeper and a western chorus frog,
Well,
and they're almost identical.
But download Merlin because like
try Merlin.
Merlin.
It's free to try.
Okay. Hey, I've not heard it.
And it's got location on there. You have to tell it kind of where you are so it knows what to look for. But
Yeah.
it's incredibly sensitive.
Oh,
Really?
I'll be sitting there and I could barely hear the bird and it's picking it up. I used it in Ireland as well. I just said, okay, my locator was on, so it says, oh, you're in Ireland. So now it knows to look for Irish birds.
Exactly. No, I was very impressed.
So like the wizard, right?
Pardon?
Yeah, Merlin like the wizard. Yeah.
Okay. No, we've been playing around with software from Wildlife Acoustics.
Well, and you also see
it sounds cool, but somebody's already done that.
Yeah. No. As a matter of fact, Cornell has an AI that does this.
It's Cornell that's behind this app.
Okay. Yeah, it's the Cornell AI that and it's free, but of course, where I work, thou shalt not use practical software. One must use horrible software, the DWIN. So we're getting a standalone. And on that, I'm going to load the Cornell software and the Wildlife Acoustics software for bats. Nobody really does frogs really well. And the biggest problem I have at work is dealing with an animal that cannot be moved.
Well,
is the size of my
bird, it
thumbnail.
won't find it.
It'll find it. That's very good.
Merlin.
So Merlin's part of the Cornell stuff. Then that makes sense.
Well, I mean, Merlin only does birds, right? So that's
see, the Cornell software, you can add creatures to it.
Okay.
I don't think it'll do mammals, but it'll do amphibians. And I'm thinking, okay, maybe I can get the frogs in there. Anyways, I was thinking of this when you were presenting it last week, Peter. I was thinking about doing this on the frog call. The argument is, and I'm droning on here, sorry. They say the animal that we have is not genetically pure. It is, in fact, a hybrid of two. And whether or not that is reflected in the call. And so I thought, well, this is kind of an interesting offshoot that might be done. We are recording it now. So. Anyways, it's an application of what you have presented that got me thinking. So I appreciate you bringing it up.
Oh, okay, good. Well, I know one thing that was neat about the Merlin is that it's got a running graph along it, or pictorial, if you will.
Yeah.
And as the different birds make different sounds, you will see how the different lines are.
It's got a sonic waterfall.
Yeah.
Oh, yeah. Okay. Very interesting.
There you go. See my clap?
Anyway,
it's pretty sensitive. You don't have to make. You can make a slight noise and it'll pick it up.
Yeah, it's extremely sensitive. I was very impressed.
And it'll run on iOS or Android. Eh?
Yeah.
Yep. Excellent.
And you don't need internet access, but then if you want to do it offline, you have to download the sound file that it needs, which is a few hundred megabytes.
Right. Which that's not a killer either. That's quite doable.
Exactly. No, it's but yeah.
We're actually targeting certain animals. We're not trying to cull out a lot of the racket and noise. That's very interesting.
It only picks up birds, so that's the restriction. But
I got a lot of birds.
Well, try it. It's free.
I will. Thank you for that. That's a great help. There we are.
Practical. Now back to previously scheduled radio programming.
I'm still waiting for the question period because I was really looking forward to it.
Well,
Dave's not here.
The real pain in the neck question period guy is not here. I'm only joking. Actually,
I know.
He said he'd be late.
We jest.
Yeah, I know. But anybody else have any questions or comments about FFT stuff?
Can you really do you think you really can do a DFT in an Arduino? Because there's no floating point.
I'm going to, well, you know what? I've seen a project that's done it and I'm going to duplicate it. So I should know in about 3 weeks. Really? I've designed a board for it and it's running off a nano. So we'll see. I've seen it in action. Now that's audio, so
Yeah, I guess. I mean, it just, I mean, you can do it with integer math too. It's just not as precise. But
I haven't looked closely
floating,
at the code.
floating point library is really, really slow. But I get, you know what? It doesn't have to be real time. That's the other thing, right? It doesn't do it in real time, does it?
Yeah.
Oh,
Well,
okay.
let me rephrase that. I don't know how much of a delay. Now, I did see a run on it, and it seemed to be doing real time.
How many samples?
I don't know.
How many bins? You know, like 500.
No, oh, well, the display was going from I guess 0 to about 3 kilohertz.
But how many hertz per
And
bin?
I'm not sure what the division was. It looked like it was fine enough to be useful.
Okay, well, even if you had like 128 there, that's still 8.3. That's still like 20 some hertz per bin. That's still useful.
That's okay. Yeah.
But because that cuts down the amount of math, then, right?
Well, it depends on what you want, right? Again, and this is a start to see what it does, and then if you decide I want to go further, well, now you got to change out the Arduino to something else.
Well, get an STM, get a Pi Pico or something that handles an ESP32. What do they run at? I'm
not sure. I figured the first step I'll do is I'll just duplicate what this guy's done, and then when that works,
okay.
The program is relatively simple enough. I haven't looked at the libraries, the library that's been done for it to see what it does. Not that I would understand it probably, although maybe ChatGPT can explain it to me.
Well, Google says that there are several libraries, FFT libraries for Arduino, and some of them are fixed point.
I think actually this library is called Fix something.
Fix FFT.
Yes, that's the library.
That's a fixed point. Yeah, that's a fixed point one. It's speed over precision, right? So that's like we was just saying, you lose precision if you're going to go to integer math.
Mm-hmm.
But there's another one that it goes up to 256 bins.
Well, it'd be an interesting experiment and see with. I've already given Michael the heads up that if it works out quite well, he can incorporate that in his audio card.
Yeah, there's an Arduino FFT that has higher precision. Oh, but if you just want to look for certain frequencies, there's one that's optimized for detecting specific frequencies.
Like a range of frequencies, or
just, one? Yeah, like say you want to detect tones from a keypad. Those are very, very specific frequencies that you're looking for. You don't care about anything else.
Oh, I see. Yeah,
there's one Hertzel. Anyway.
Yeah. Well, like I say, we should know next month sometime, hopefully. Board should be here in 2 weeks. The display, I think, is another week out. And there's only a handful. There's only like a couple of resistors in the cap, and that's it.
And this is for what?
Audio frequency, just FFT.
FFT on audio. So you just feed in an audio display, and it just gives you
It gives you the FFT display of the audio signal.
How do you get the audio into it?
Cable and a jack. It goes in the A0 input pin.
Okay. Just straight in though.
Yeah.
You can hook your active probe to it.
Actually, I watched that. Was it AEW? No, it was IMSI guy, the active probe thing.
Yes.
When he had his 2 gigahertz probe versus a 1 gigahertz probe versus a 500.
There's some eye openers there.
That was very eye opening. Yeah, I had no idea it was that bad. Yeah. When are we building these active probes again?
Well, I think, Peter, that active probe coupled with what you're describing here leading to something fairly powerful, because your probe is the trick that makes it work.
Well, it's interesting. Well, you know what? The probe down at audio is going to be really high impedance.
Yeah.
It should be terrific in that regard. But it's
yeah.
But I kind of wish I made my comment about what Einstein guy did the other day there, because there was something that he did that I don't think was really right. Like he left something off, but I can't remember. I guess I have to watch the video again in order to. But it's interesting. He for the first time, I'm seeing he's starting to attract a little bit of negative comments that I have not seen on his channel before. But well, hopefully he's got thick skin.
There seems to be negative comments available for anything that shows up.
Yeah, he's he's getting popular enough that the bots are kind of honing in on him, right?
Makes me wonder.
Well, he puts out these, most of them are relatively short, and that's good. And it works, and they're out daily, and I watch it over my morning coffee.
When I remember,
it's pretty hard to produce a video a day,
Oh God! Well, I think he produces several in one particular day, and then.
Oh sure, but that's a lot of content.
Oh, it is. Yeah.
With editing and everything else.
Oh yeah, I don't think he edits that a lot much. Not like some of the other guys. But and he got shit for that the other day too. You made a mistake in what you were saying early on. You should have restarted and redid it and all this kind of crap. But anyway.
Oh
yeah, well, there's always those guys.
Yeah, I mean it's easy to say when you're not having to do all the work.
Yeah. Well, one of his mentors is that he wants to produce a raw video and where you would see the mistakes and what went right, what went wrong, all in real time, and not a heavily edited video like you get a lot of, which is fine.
There's a lot of honesty to that.
Yeah.
And editing video is not a trivial task.
No,
sure. It's not.
Anyway. So, got lots of time left. Any other topics anybody wants to bring up or questions?
It's not a cool chip, but it's like I was looking at something and it's like I didn't know this kind of stuff. Well, I knew it existed, but not exactly. And I was thinking of it for our. I'm going to find my notes here. Oh, there we go. I was thinking of it for our SNA when we built that shield around the 8307.
Yeah.
Hang on. Get this link up here. I wasn't prepared for anything. But I couldn't find this exact product, but they have a whole line of sort of pre-made stuff. So here, I'll put this in the chat. It'd probably be easier if everybody can see it anyway. But when we'll share my screen.
Are you sharing what you just put in the chat?
No. Yeah.
Oh, yeah. Okay.
Yeah. Let's see. Chrome tab window. No. Oh, that's it right there. Okay, I didn't even recognize it. Ignore all the ads, but it's got like these. Well, they call it origami shields, and it's made by Worth.
Don't see it yet. Oh, there we go.
And they have. Crap. Anyway, it's like to have it. It's like when we did the SNA, we all had a piece of little brass. And you had to fold it and solder the edges, and and then try and get a good connection all the way around on this. So, but they make these, and I don't know if I can blow it up enough. No. Yeah, no, it fails. They make like a pre-scored sheets, which I could not find a DigiKey. But they also make pre-made little boxes, and they've got like solder tabs and and things like that, and they're different sizes and depths, and they've got frames and everything. They've even got frames that you can that you can use to put around components, and then the actual cover snaps onto the frame, so you can still get at it easily even though it's not, the frame is soldered, but the cover is not.
Oh, the cover just pressed
Yeah,
it
just
over the
let
frame.
me give me
Okay.
a second here. I'm gonna call it up. I just thought that was kind of neat because I hadn't really looked at this stuff, and we know that putting shields around this stuff matters, right? For some of this RF stuff, if we're talking, let's see if I can get it. Sorry, I'm trying to find. Oh, there it is. So I'm not sure which one I'm sharing here. Okay, yeah. So you see that now?
Yes, from Worth. Yeah.
Yeah. So it's like this little envelope of stuff, like brass or whatever. No, nickel, silver. Okay. And it's $30. Well, how big is it? 200 by 150 millimeters. And it looks like it's pre-scored. So if you have to do shielding, you can buy this little envelope and then just cut and form it. But they've also got the preformed shields. Anyway, just something that hadn't run across, hadn't thought about. RF shields, there we go. And so they've got, they've got like little covers like that, right? That don't actually solder onto the board, but then they've got a frame that goes with it that does solder on.
What are they worth?
$2.
Okay.
90 cents, $4, $1.71, depending on the size. I don't know what. So something like, yeah, there's tons of sizes for everything you want. It looks like.
Didn't know they
like
existed.
A 1/2 inch by a 1/2 inch is $4. By the time you fool around cutting something and everything else.
Well, you'll spend 2 hours doing it, and it'll be a half job.
Yeah, and this is a professional looking job. Anyway, it's not a chip, but it's still something useful, especially if we're doing low noise RF.
That's for sure. And when you think about how much time you fool around with, like I'm thinking back to when we were doing those little brass boxes and all the time messing around with it, and it looked ugly for $4.
And if you have to fix something inside there, it is a nightmare to get the thing off, and then you have to rebuild it to put it back when it's working.
Yeah.
And you can get versions of these that are have perforations, so they'll actually let some ventilation through. So as long as we're not doing gigahertz, then it doesn't matter, right?
Right. Yeah. That's right.
Anyway, that's me. Stop sharing. Anyway, that's my. That's a semi-cool chip, sort of.
Cool chip protector.
Cool, yeah, cool chip, yeah, a cool chip protector.
Oh, that's good. Anybody else have any comments or queries on anything?